Now, as you see, the title to this webinar is actually Introduction to RMC Feedback Types. Originally, we wanted to show everything that the RMC can do as far as feedback, but quickly realized there's just too much information to fit into an hour. So rather than cramming it all in, we've decided to split it up, and this is going to be more of an intro, looking at our most commonly used feedback types, some of the background behind them, and just some pros and cons to each. So for more information on using RMCs, you can refer to our Delta video series. This is a great little training sequence that basically will quickly take you through in just about an hour and give you a really nice understanding of how RMC tools works and some of the basics behind it. It's great as a first introduction or as maybe a refresher. Possibly you took an RMC tools training course a year ago and now you have a project. Well, these Delta videos are a great introduction. Also, if there's parts of RMC tools that maybe you don't understand through this webinar, really encourage you guys, reach out, ask us questions. We're always happy to help, but if you'd rather go through something on your own time, this video series is a great tool as well. Now, for more webinars like this one, we've got a pretty extensive library now of webinars. You can look at some of the titles here. Some are more, I would say, introductory, such as this one, and others really dive deeply into an application or a specific concept. But just about anything you'd be curious in, we've got a webinar that's going to touch on it. Okay. So the topics that we're going to be covering today, what do we want in feedback? What do we want to try to avoid in feedback, right? So this is going to be the first topic we're going to cover. What consists of good feedback in our opinion for motion control, and what are some drawbacks or things that we really want to try to avoid? And then how do we get this ideal feedback? So here are some of the feedback types we're going to talk about. SSI is a big one. This is one of our favorite feedback types. MDT, you may know it as start-stop or PWM. MDT is kind of a blanket term that Delta uses. Analog feedback, quadrature, and resolver and communications. So the resolver and communications are two feedback types that we're just not going to have enough time to really dive deeply into today, but those are two options that we have as well for feedback. Okay, so what do we want in feedback? Well, the first thing that we're going to be looking for is high resolution. We want low noise, and we want our feedback to be synchronous, as well as we want a fast update rate. Now, with each of these, you're going to have really nice feedback. One thing I want to note before we get deeper into this is what's ideal. It's not necessarily always what you have, and that's okay. There's lots of options that we have within RMC tools and the Delta RMCs that allow you to function with maybe feedback that isn't quite ideal. But if you have the option and you're designing something up from scratch, these are the bullet points that we really want to hit with your feedback. So what's the difference between synchronous and non-synchronous? Well, I think it's best to just show an image here, and we'll dive into why these are looking different here. You can see on our left here, we've got an image of a synchronous plot. This red line here is my position, and this blue line here is my actual velocity. You can see with the synchronous example, the actual velocity it's fairly steady. There's a little bit of noise, but it's nothing really crazy. You can see here with the non-synchronous version, your velocity is jumping all over the place. Your position is still fairly steady, but your velocity here, it starts to cause us some issues. So the reason that this is happening is because with a synchronous controller, or a synchronous feedback rather, we're getting position data at known time increments, right? So if we have known time increments before our positions, we're able to calculate a velocity that's very consistent, like the velocity we see here. Without that, without the known increments, if we're kind of getting them randomly within a window, well, the velocity calculations, they start to jump back and forth, and this can cause problems with control. And we'll talk about some of those problems as we go, but you can see here, there's a big difference between synchronous and non-synchronous feedback. So why is resolution so important? Well, of course, right, the obvious reason, if you want accurate position data and accurate position control, you're going to need high resolution. The controller can't hold a position if it can't accurately determine how close it is to that desired position, right? So if you want to hold within a thousandth of an inch, but your resolution is a thousandth of an inch, you're going to have a hard time actually getting there because you're going to be plus or minus, and there's not really much granularity as you get closer and closer to that target that you have there. It's generally necessary to have resolution that's several times better than the desired accuracy. So again, back to the example, if you want to get within 1/1000th, and that's the same as your resolution, it's going to be very difficult to get there. So you're going to want something that's several times more accurate than that thousandth of an inch. So position accuracy is important for controllability, even if accuracy isn't important. This is something that's very good to note because a lot of times you might think, well, I don't really care about the accuracy all that much in my application, so I can get some subpar feedback and maybe it's not going to affect me. Well, in some cases you may get away with that, but in other instances, let's say you have a system that's just difficult to control, that lack of feedback, of good feedback, is going to come back to bite you. It makes it so much easier to tune up a system and control a system when you have good feedback. And we're going to dig into this more as we continue on. But just remember, it's important to have good feedback and high resolution, even if you don't need high accuracy in your application. This is something that's also important to note. High resolution is a requirement for, but is not equivalent to high accuracy. So if you have great feedback, but your valve maybe is maybe just a cheaper valve, perhaps it's not really suited so much for motion control, well, even though you've got this wonderful feedback, you're not really going to be able to get to where you need to be. A great example is like a race car with wagon wheels. You've got all that power, but you're not really able to use it to go anywhere. That's kind of what it's going to look like if you have great feedback, but your system isn't set up to really take advantage of it. Quantization is another reason why we want high resolution. So what is quantization? Well, since velocity is the change in position per unit of time, the velocity resolution, it's dependent on the position resolution and the controller loop time. This is going back to that synchronous versus asynchronous. These kind of play into each other, right? You're going to get things that look somewhat similar. So again, we're getting position feedback, we're not getting velocity feedback. And so our velocity is going to need to be calculated based off those position points that we're getting. And we're calculating it, as you can see here, right? We measure the change in X and we measure the change in time. And the equation probably everyone's familiar with, velocity equals change in X over change in time. So this is what we're doing to determine our velocity. So let's look at an example. If the controller has a 1 millisecond loop time, the velocity resolution will be 1,000 times worse than the position resolution. And the acceleration measurement will be 1,000 times worse than the velocity measurement. So you can see each step, right, we're getting 1,000 times worse. There's 1 millisecond loop time, right? So 1,000 measurements a second. And so 1,000 times worse for the velocity and the acceleration is going to be 1,000 times worse than the velocity. Let's look at why this happens. So velocity max error equals position max error times samples divided by period, right? Samples per period, 1,000 samples per second. Velocity max error equals position max error times 1,000. So that's where we get our velocity error increasing by 1,000. And then you can imagine that same equation being applied, going from velocity to acceleration. So you just get more and more of this quantization error. Now, why is this important for control? Well, the differential gain and the double differential gain use the actual velocity and actual acceleration to increase the system stability. So excessive noise is going to really limit the effectiveness of those gains. To make this more clear, let's look at the equation for differential gain. What does the differential gain actually look like? Well, the differential output is going to be your velocity target minus your velocity actual times your differential gain. So you can see here that when we have a velocity that's 1,000 times worse than our position, your differential gain is going to be working off that, and it's going to have a tough time. And it's even more difficult with your second derivative or double derivative gain. That gain is going to be looking at your difference between target and actual acceleration. It's a very useful gain, works wonderfully for systems that are just not ideal or are prone to oscillate at the start and the end of moves. But if you don't have high quality feedback, you're just not really going to get any good acceleration data, and so you're really not going to be able to use that double differential gain. So if you have a system that's tough to control, even more we recommend try to get high resolution, good feedback. So how do we achieve ideal feedback? Well, funny enough, a lot of times it comes down to grounding, especially with analog feedback. It's kind of funny, but you would be surprised at the amount of times we see the analog minus pin is connected, but the ground pin on our RMC, it's just left floating. And so sometimes that analog feedback is correct. Sometimes it just loses control. Sometimes it's just very noisy, but you really want to make sure that you are grounded, or you'll be fighting with phantom problems, and you may be able to get something that's controlling, but that's always the first thing we check if you're seeing excessive noise on your feedback. Check your grounding. Shielding is important as well. Make sure your cables are shielded so they're not picking up all that electrical noise that's going on, especially in an industrial environment. If you're close to a motor or something, make sure that your cables are shielded. Also, having twisted pairs is a wonderful way to reduce that noise. We have a great webinar that goes over some of the wiring and kind of why these twisted pairs are important. We also have some other videos. So if you're interested in those, we've got a wiring and setup video for wiring ground balance, wiring differential analog inputs, and we also have a nice webinar. There's a great deal of information on Delta's website, and if you're wondering, well, what's ideal with wiring? Is my setup okay? Feel free, give us a call, send us a message. We're always happy to help with stuff like that. Okay, so let's talk a little bit more about feedback types and the actual technology behind these. What makes it run? And by understanding this, hopefully it helps you troubleshoot some of these technologies a little bit better as well. So how do magnetostrictive sensors work? Excuse me. So here's a nice little cutaway of a magnetostrictive sensor. Inside the probe, there's a rigid wire made of magnetostrictive material. So you've got a little wire that's inside this probe here. Torsional strain or twist is introduced in the waveguide. This is from this magnet here that you've got that's going to be moving, and it's going to be telling us the position. And that twist induced on the rigid magnetostrictive material here, that is carried down. That travels down the wire as an ultrasonic wave, and it's moving approximately 2,850 meters per second. And that twist or mechanical pulse, it's detected by the signal converter. And what that does is it tells us, well, where's the magnet? So this is a great technology. It's used in a lot of SSI transducers. We usually say MDT, but start-stop, PWM, it's used in a lot of different transducers. And if you have a transducer that goes inside a cylinder, there's a very good chance that this is what you're going to be using. Okay, so with this technology, there's some limitations, right? Magnetostrictive transducer lengths. An MDT transducer takes a certain amount of time to determine its position, right? We need to wait for that mechanical twist to come back. It's just, based upon the physics of how the design works, it's going to take some time. And that time it takes is going to increase with position. So therefore, the length of the transducer dictates the minimum loop time you can have, right? If we're requesting new feedback every millisecond and your transducer doesn't have new feedback every millisecond, well, there's a problem there, right? So what we can do is increase our loop time if that's what's needed with the transducer. We also have a nice formula for determining the loop time. And that's going to be length equals loop time, milliseconds minus 0.22 divided by 0.0095. But if you don't want to go through and calculate this formula, we also have a nice little table that gives you some different lengths that we can use with our loop times. So you can see here with a 500 microsecond loop time, you've got about 30 inches of travel. 1,000, you're at 82 inches. And then all the way at 4,000, right, you're very close to 400 inches. So these are your options. Generally, you're not going to have a transducer that's greater than 400 inches. And if you do, maybe MDT isn't the right option. There's ways that we can kind of get around this, but you might want to use something else, and we'll talk about those other options as well. Okay, so let's talk specifically about what we call MDT feedback. This is going to be the start-stop or pulse width modulated. These MDT, magnetostrictive displacement transducers, they're absolute position, and they're used in a lot of rugged industrial environments, right? You can see this picture here. Here's a Tempesonics MTS transducer that's going to be set up to go inside a cylinder. This is a pretty common transducer that we would work with. Early MDT sensors, they usually employ the start-stop or pulse width modulated, and this is what we call MDT. But again, as time goes on, they developed other types as well, such as analog or SSI. So what does MDT feedback look like? Well, the RMC's internal counter begins to count when the first pulse, start pulse, right, is received, and it stops counting the second pulse when the stop is received, right? So this is a start-stop. You basically get two pulses, and if you were to hook up an oscilloscope, this is what you'd see. You'd see a pulse here and a pulse here. The time between the start pulse and the stop pulse is proportional to the transducer position, right? So if you have a position that's very small, your start pulse and your stop pulse, they're going to be very close together. And as that position widens out, well, the start and the stop pulse, they're going to start to widen out as well. So to make a measurement with a start-stop transducer, the RMC is going to send an interrogation pulse to the transducer. So this is kind of the full picture, right? We send an interrogation pulse. This is coming from our RMC. This is going to the transducer, and this lets the transducer know I need to respond, right? So the transducer responds by returning two pulses, the start pulse and the stop pulse. And those same pulses that we were just talking about before, right? So the start and the stop pulse, they both get sent. And you can see here, this is when our counter is active. We're counting in between these two pulses, and based upon the time here from our counter, we know the position. So the other option we were talking about is PWM. It's very similar to what we were seeing before. Again, you're going to send an interrogation pulse, right? This interrogation pulse comes from your RMC. But we get a different return signal. The return signal is high while the transducer is determining its position, right? So instead of a start pulse and a stop pulse, you just see this signal here. And pulse width modulated, if you're familiar with what a pulse width modulated signal would look like, maybe for controlling LEDs, well, you know that pulse, it'll change lengths, right? It'll go anywhere from 0 to 100%, and it's continually pulsing. Well, that's the same with this transducer here. You've got a pulse that's changing how long it's active, and you can see our counter is active the entire time that return signal is on. Okay. So what RMC module would you use for MDT feedback? Well, the RMC 75, it's got an MA module. Two MDT axes are available with this MA module here. RMC 150 has an option as well. MDT module, two MDT axes as well there. The RMC 200, it's got an S8 module with 8 MDT inputs. So this module here could be used for up to 8 MDT inputs. And then you also have an option with the U14. That's two MDT axes. So we've got images here of the S8 and the MA2 on an RMC 75, but each of our controllers here with the latest generation, they're able to do MDT feedback. There's a couple more things to keep in mind when you're choosing a RMC module. The resolution of the MDT sensor depends on the RMC's clock speed for timing the pulses, right? Which makes sense because that's basically what we're doing. We're timing in between our pulses, and then we calculate a position based off that. So here's a quick little table of what we can do with different controllers here. You can see RMC 75, 200, and both 200 modules. They're all pretty much all the same. Maximum resolution with one recirculation is 0.0005, and then the RMC 150 MDT, it's a little bit less, 0.001. That's with one recirculation. Okay. Now, what I want to do is show you a live example that I have here. So on my desk, let me bring this little video over here for you. It's a little bit tough to see because there's sunlight right now coming through the window, but I've got 3 transducers here. I have a SSI transducer from Balluff. I have a analog transducer from Gemco, and then I have a PWM here from Tempasonics. What I'm going to do is go ahead and I'll move this PWM sensor. We're going to see it back and forth on the screen. So let me take my RMC Tools project, bring it here so that you can see. Let's make this a little bit smaller. There we go. So I've got 4 axes right now set up on my RMC. Let's look at what the PWM setup is going to look like. So I can see right now when I'm moving this PWM sensor, you can see the feedback, right? It's moving back and forth, and it looks like everything is working just fine. If you were to set up a sensor like this, what you do once you had your axis configured, you would go over to your axis tools, go to your MDT axis, and then what I would do is go to my feedback section right here. I've got it set up to display in inches. You can see I've set the feedback type for MDT. You can also change it to SSI for the S8 module that I have on my RMC 200. I can change the MDT type, so PWM, start, stop. I can change the blanking period. So if you have, say, an older MDT transducer, sometimes the blanking period needs to be a little bit longer, but usually this 5 microseconds works just fine. And then I've got a position scale that's been set up as well. I went through my position scale offset wizard. I just used the gradient that I saw on the side of the transducer. And you're able to get to this point where you've got this nice feedback set up and it's ready to go. Okay. So let's talk a little bit about SSI feedback. What is SSI feedback? Well, it's synchronous serial interface is what SSI stands for. Data from the sensor is encoded in a binary or gray code format, and it's transmitted over a high-speed serial interface. So what does this actually look like, right? To read an SSI position, the RMC is going to send clock pulses to the transducer, and the SSI is going to return data. So the RMC, we're sending clock pulses here. The SSI channel sends the first clock pulse by setting the clock signal low, then high. So again, if you connected up an SSI transducer to an oscilloscope, this is what you'd see coming from the RMC, this clock signal here. On the first rising edge of the clock signal, right? Remember, first we set it low, then on the rising edge here, the SSI transducer is going to return the most significant bit of the data on the data line. So that most significant bit here is going to be sent. This is from your transducer. So that transducer is sending the data back to the RMC, that most significant bit. The SSI channel is going to send the second clock pulse by setting the clock low and then high again, right? So if you're familiar with a clock pulse, just low and high, it just looks like this little square wave here. And when the clock signal goes high, the SSI channel is going to sample the bit on the data line, right? So you've got the data going back. And when the SSI device sees the clock signal go high, it places a second bit of data on the data line, right? So each of these bits, they're going to be sent back, and this is how we're receiving data. It's a digital signal. This continues until all the bits have been clocked and sampled. So for instance, if you've got 24 bits, you're going to see 24 bits here that's coming back to your controller, and that's going to happen every single loop time. So the value obtained from the SSI data is then going to be put into the raw counts register here for that axis, and then the raw counts are going to be converted to counts and then into actual position and user-defined units. Now, you don't have to really go through any of the calculations here. We've got a very nice scale and offset wizard that you can go through. And basically, all you need to do is write down the resolution of your transducer and how many bits it's using. Very easy setup. So what are the advantages of SSI? High noise immunity. SSI is great. It's got the twisted pairs or paired feedback just by default. Absolute position, you're always going to see the absolute position, so you don't need to worry about homing. Very high speed, supports a wide variety of transducers, right? If you need a linear transducer or a rotary transducer, it's usually an SSI option. And it's a very cost-effective way for data transfer. Only one 5-wire cable with a shield is needed. and many SSI devices offer high precision. For example, 1 micrometer is not uncommon. Some offer 0.1 micrometers. So you can get very, very accurate feedback with these SSI transducers. The transmission rate is independent of data length and resolution as well. So you're always going to get that transmission back when you need it. And it's very good for transmission over long distances. So the SSI, as it sits right now, is our favorite feedback to use. If you have the option, we usually try to go with SSI. It's going to make your life a lot easier in the future. Say you need to use the second derivative gain for one reason or another in your system. Well, if you have a nice SSI transducer, that's going to be an option. If you have an analog feedback, a linear transducer with analog feedback, you're probably not really going to be able to use that second derivative gain very effectively. So what RMC modules can you use? This is going to look familiar. The RMC75, you can use the MA module, 2 SSI axes. RMC150, you can use the S8. There's, or I'm sorry, not the SSA, the S8. You can use the the SSI module, and that's going to be 2 SSI axes. The universal I/O also has 2 SSI inputs. The RMC200, you're able to use the S8 module. So this S8 module right here, 8 SSI inputs, or the U14, 2 SSI axes. Now, you probably remember this from a few slides back when we were talking about MDT. That's because we set it up so that our modules can work for SSI or MDT in most cases, definitely with the RMC75 and the RMC200. So here's a little bit more information about what module you might want to use. You can see that clock rates, you've got a few more options with the RMC200. 75 has a few options. There's different things here. Most of the time you're gonna, you'll find something that will work just fine with your transducer, but if you need a kind of different clock rate, maybe something not very standard, it's worth looking into the different modules. You're able to do binary or gray with each of these, and most of these you've got 8 to 32. With the RMC 150 SSI, you've got 8 to 31 bits, but generally you're going to have 8 to 32 bits. Okay. One more thing to note here: the S8 here and the RMC 200, you're able to ignore high and low bits. This is kind of a neat feature. For instance, maybe some of the high bits are used as error codes. Well, we're able to ignore those and not treat them as feedback with the RMC 200. Okay, let's look at my live example. I'm going to show you how the setup is done here with an SSI transducer. And let's look at our plot here. So here's my SSI axis. And my SSI transducer is the BALF one here. So you can see moving that magnet. You can see it's moving back and forth. It's working just like we would expect here. I don't know if you saw that. It's kind of that data where it bottoms out right there. That's because I brought it too close to the head. You can kind of see that velocity, it just bottoms out as well. So you want to keep it, of course, keep it in the range where you're actually working, but you can see it works just fine. Let me show you what the setup would look like here for our SSI axis. Display units, right? I've got it set up in inches. Feedback type is SSI. Could change it to MDT. SSI format, the transducer I have is gray code. Gray or binary, both work just fine. SSI data bits, this particular sensor has 24 data bits. And my clock rate set to 100 kilohertz, which is just fine for this transducer. And you can see my position scale. All I did here, go up to my position scale offset wizard, click launch, transducer or encoder, next, linear transducer, next. Set up my desired position unit, which for me is inches, and then the transducer resolution. This is a 1 micrometer transducer, and I can put in an offset here as well. And you just choose, would you like increasing counts to equal increasing position or decreasing position? So totally up to you as a user. Next, you can see that it's calculated my value here. Next, and finish. And you've got nice position feedback. Now you can see that I'm at 6 inches here, and that's actually where I am as well. It might be a little bit hard to see from the video, but yeah, I'm just about 7 inches out. Okay. So what is analog feedback? This is probably the one that's the easiest to understand. Very clear on what's going on, really easy to measure with a multimeter. You can go out there with your multimeter, you can check to see, well, hey, do I have 5 volts of feedback or 4.5? Is everything looking like it should be? But the definition is that it's a time varying signal conveying information, right? Usually through voltage or current. So our digital signals like SSI, they look more like this. Our analog signal, it's going to look more like this. Okay, resolution versus length. Let's talk about analog transducers and resolution versus length. This is an important one. So I'm going to give you 2 examples. Example 1, transducer feedback 0 to 10 volts. That's pretty common. That's what I've got set up right now with my Gemco transducer. We'll say the length is 10 inches. And the resolution of our measuring device is 18 bits. So our resolution is going to be 10 inches divided by 2 to the 18th, right? Or 0.000076 inches per count. This is kind of what we care about. You can see, well, that resolution looks pretty good. Now, example number 2, we've got the same transducer feedback, 0 to 10 volts, but our length is 1,000 inches. Now, this is a pretty drastic example, but I just want to show you the difference. Resolution of our measuring device is still 18 bits. So our resolution is going to be 1,000 inches divided by 2 to the 18th, or 0.0076, right? So it's 100 times worse than what we were seeing before. It's just going to be harder. It's going to be much harder to control to a very precise, say you want to control to 100th of an inch. Well, it's going to be a lot more difficult with this second transducer than it would be with this first transducer. And it's just something to keep in mind with analog feedback. Works the same with, say, pressure transducers. If you have a very, very large range on your pressure transducer, and maybe you don't need that large of a range, say you go to 100,000 pounds and you want to be measuring plus and minus 5,000 pounds, and you want to hold within a tenth of a pound, well, maybe you don't want that 100,000 pound pressure transducer. So your 2 options with analog feedback are current or voltage, and there's pros and cons to both. Generally, current is going to be lower resolution, not always, but generally that's kind of more what we've seen. It's more immune to noise over long distances, and it's used more in process control, generally speaking, than motion control. Voltage, it can have higher resolution, easier to verify with a multimeter, and used more widely in motion control applications. So a lot of times you're going to see that you'll be using voltage feedback, but current feedback is a definite option as well. And it really just depends. You need to look at the data sheet and see what you're getting from the current or the voltage transducers. Okay. So what RMC module do you want to use? Well, you can see with each of our controllers, again, we have many options. Here's an AA2 from the RMC 75, and here's an A8 from the RMC 200, but whatever controller you choose, you're going to have options for analog feedback. All right, let me show you my transducer. Okay, here's our analog 0 to 10 volt. And this is our Gemco transducer here. You can see I'm able to move it. Everything looks fine. And you know, it's very difficult to see between these three transducers when it's just, them plotting against each other, which transducer is better. And you really have to dive into the details, and it's very difficult to see with your eye that you're going to be able to control a much more precise system with the SSI versus the analog, because, this analog plot, it looks very similar to my SSI plot here. You can't really see a whole lot of difference, but there actually is quite a great deal. And if we were to really zoom in here, you'd see basically what looks like the difference between synchronous and asynchronous, right? That those plots that we were seeing at the very beginning of the webinar. So let me show you the setup here for our analog. Display units, right now it's in position units. Probably want to change this to inches. I set up my analog input type, plus or minus 10 volts, or for this A8 here, I also have the option of using current 4 to 20 milliamps. My analog limits, I've got a plus or minus 10 volt, I'm sorry, a 0 to 10 volt transducer, so I've got my analog overflow limit set at 10.1 and the underflow set at negative 10.1. Analog input filter, 4 kilohertz. You can change this to whatever you like here. This is the least filtered option, and it's the default. And then you have a position scale as well. If you have your transducers data sheet, you're probably able to find this here. I just kind of threw this one in here. It looked like it was about a 24-inch sensor, and so it's roughly in about 4 inches away from its head here. Okay. Now, the last feedback that we want to talk about today is quadrature. So what is quadrature? Quadrature encoders are one of the most common types of encoders. So you're going to see have a rotary setup generally with quadrature like this. Quadrature encoders are incremental, and they're commonly used to provide a reference input such as position of a belt or position of a board on a flying cutoff application. So, you're usually going to see this, right? Something that's rotary feedback. Reference position is a very common way to see these quadrature devices. So what does quadrature look like? Well, you've got an A signal here. This is going to be coming from our transducer. And you also have a B signal. So you've got your A signal and your B signal. And as the transducer spins, it's going to put a waveform out to our RMC controller that looks like this. Based upon this waveform, we're able to tell, are we incrementing or are we decrementing from the position that we started at? Now, you also have, in many cases, an index or Z-pulse. And generally, you're going to only see the Z-pulse once per rotation, right? So if you have a rotary transducer, the Z-pulse is going to be high once per rotation. You can use the Z-pulse to do things like you could home off a Z-pulse, or you could count and say, I've gone around once, twice. There's different use cases for it, but you're generally going to only see the Z-pulse once per revolution, and the A and B pulse, these are going to be constantly going up and down. So here's a cool little image of an oscilloscope. This is what we would see. Number one, it could be the A or B. Number two could be the A or B, right? They're going to look very similar. And then number three is going to be our Z pulse here. So how does quadrature actually work? Here's a cool little explanation of how the controller is able to determine how, are we incrementing or decrementing? If you're familiar with the idea of a state machine, here's a simple one here. And let's just go through, one case here. So I'm going to say that we're at 1, 0. So if I look on my chart here, I can see that I'm at 1, 0, right? A is high, or 1, and B is low, or 0. So we're right at this point. Well, let's say we go over to our right. What happens? We went to state 1, 1. And so since we're going to state 1, 1 here, you can see, well, how do I get from 1, 0 to 1, 1? Well, I have to follow this path here, and that's the increment counter path. So following this is the logic inside the controller. I know, hey, my position units have increased. Versus, let's say I go from 1, 0 to 0, 0. Well, how do I get to 0, 0? Here's 0, 0 here. I need to follow this path, or the decrement counter path. And so I'm able to get from one state to the next, and I'm able to know if I'm decrementing or I'm incrementing. It's very simple, but it's a very effective and a great way to count and know where you are. RMC and RMC 150 quadrature inputs require RS422. These are going to be those 5-volt signals, lower voltage. RMC 200, they support a little bit more. We can use the RS422 differential. This is what we recommend, but we can also do TTL single-ended or HTL single-ended and differential. Generally, we like to stick with RS422, but if you have different voltage levels on your quadrature encoders, we're able to use these as well with the RMC 200. RS422 is also commonly referred to as a 5-volt differential signal, so it's going to be that lower voltage signal. Delta recommends RS422 line driver outputs for quadrature encoders as it provides the highest speed and very good noise immunity. Really immune to noise, higher speed, you've got lower voltage changes, just a nice way to do it. But again, TTL and HTL, they're supported by the D24, Q4, and U14. And they're really only intended for retrofit. So if you've got a new application, try to stick with this RS422. But each of these modules, the D24, Q4, and U14, they're all RMC 200 modules. So one problem that we have with quadrature is generally we need to home it. Absolute position is not provided, right? We've basically got that state table. So if you power up a machine, all you're getting is, say a 1 from the A and a 0 from the B. You don't really know where you actually are. You just know if you're incrementing or decrementing. So a known reference point must be established, that home position. Generally, you're going to increment or decrement until the home position is reached. And once the home position is reached, the actual position is changed. So we can change this in the software. So what that might look like is, I'll move the transducer until, say, we see the Z pulse, or move until we go to the end of our travel, and then wait for a little bit and call that home. There's many ways you can do it. Maybe a limit switch. All kinds of different ways you can go to your home position and find it, but generally with quadrature, you're going to do that on startup. So what is quadrature registration? You may have heard this term or you may have not, but registration is the process of recording precise position of an axis when an external event occurs. So let's look at an example. Consider a photo eye setup, right? You have a photo eye on a conveyor belt. Maybe there's a part going down this conveyor belt, and when that photo eye signal is broken and reconnected, both those points are stored, right? So you can see, hey, this is where that part started and this is where it stopped. Well, registration allows point saving in between loop times. So what this means is that you don't get shoved off to the closest millisecond, closest loop time, right? You can actually save those times in between. And one more thing I want to note, saving those times in between means that we can have very, very accurate measurements, and much more accurate than we could with other feedback types. So if you want extremely accurate measurements between 2 points, something like the example presented here, quadrature is a great option. So what RMC module to use with Quadrature? RMC 75, we've got the QA, QA1 or QA2. This is a 2 quad axis controller, or module rather. The QA1 expansion, you've got 2 Quadrature inputs as well. The RMC 150, you've got a Q module with 2 quad axes, and the UIO can also have 2 quad inputs. RMC 200, you've got the Q4 module, which is 4 Quadrature inputs. The S8 module, 2 quad inputs. And the D24, which is 2, and the U14, which is also 2. So you've got lots of options with each of the controllers. Let me show you the Quadrature that I have set up here. Let's see if I can move this a little bit just so you can see it. There we go. Okay, so I have a Quadrature encoder here. Let's look at my quad axis. So I can spin this around, and you can see that it's spinning. It's going up to a point and it's jumping back down. Right now I have it scaled so that it goes from 0 to 360 degrees. This is how my Quadrature encoder is set up. You can see when that's spinning, we've got our feedback here. Now, if I look at setup options, axis tools, I can set my display units. We'll set this for degrees. Is this a linear or rotary? I said this is a rotary axis. Position unwind. This is what I want to actually, see at the end of the day, and that's 360 degrees. That's what I'm seeing. And then count unwind. Well, how many counts am I getting, right? Those are those A and B pulses. How many of those changes am I seeing when I do a full rotation? And for this Quadrature encoder, I've got 2,000 counts per revolution. And then I've got my counter mode as well. You can choose with the RMC 200, I can choose, do I want A quad B, pulse A rising, pulse A falling, pulse A both. So you can use it kind of as a pulse counter rather than a Quadrature encoder as well. And the encoder that I have here, it's not RS422, it's actually differential HTL. And I do have a Z pulse as well on here. So that's basically how you'd set up your Quadrature encoder. Very quick and easy to do. Not a whole lot that needs to be done for the Quadrature encoders. Okay, so that was a lot of information very quickly. But just to summarize, Delta has quite a few great options for feedback. You can see each of our controllers can handle any of those feedback types that we talked about. SSI, MDT analog, Quadrature resolver. Generally it's going to be that SSI, MDT analog or Quadrature, but the resolver is also available with the RMC 150. Maybe we can do a webinar sometime in the future on that. But the setup is pretty easy, right? We went through what it would take to get each of these set up. It really doesn't take too much time. You just want to make sure that you've got the data sheet for your transducer. And we've got tools for working with each of these different feedback types. So I want to talk a little bit about controller options. If you're not familiar with our lineup, the RMC 75, you've got 1 to 2 axes of control. So great for smaller applications. The RMC 150, 2 to 8 axes. The RMC 200 Lite is up to 18 axes, and the RMC 200 is up to 50 axes. But one thing I want to note is that all these controllers, they use the same software. The setup would be exactly the same. Just the RMC 200 has a few more options. As we kind of went through, you saw some of those little options that you've got with the RMC 200. Delta has a lot of resources as well. And really what I want to emphasize here is if you have any questions on feedback or anything control related or Delta related, feel free to reach out. We've got really knowledgeable Delta sales team, tech support team, and distributors. We've got good application docs if you've got something more specific. We have examples for those as well. And then we also have hydraulic design guide as well. The last thing I want to mention is if this was mostly a review for you, you said, well, I already know most all of this information. We've got a great advanced training course as well where you can actually come out here to Delta. You can get some hands-on time with our whole Delta lab setup. We've got, I think we've got 12 physical systems right now that you can work on. There's presses, there's cylinders, there's kind of a swing arm pendulum type system. We've got a Stewart platform, all kinds of fun stuff that you can work with. And we spend a few days and we go through it all. And you get plenty of time to talk to any of the engineers here. So were there any questions, AJ?
There absolutely is a question. There's a question from the audience. Can I see the first slide of SSI feedback again? So would you mind flipping back to that
Yeah, let's
screen?
jump back here. Let's see. This one here? Or possibly this one?
Yeah, I think that's the one right there.
Yeah. One other thing to note, just in case anyone else has a similar question, we're going to publish this webinar as soon as we're done with it. So you'll be able to find it on our website and find it on our YouTube channel as well. And you can, look at any of these slides as long as you like. Okay. All right. Was that it for questions?
That is it for questions. Thank you.
All right. Well, I'll let AJ take it away with the hydraulic design guide then.
Thanks, David. Great presentation. Appreciate it. Yes, we have a free hydraulic design guide available. It is a 64-page booklet. If you go to deltamotion.com, right on the home page there, you'll see this icon with the free design guide. Click on that. We'll ask you to enter a mailing address. Somebody from Delta will contact you to confirm the mailing address, and then we'll send you a free copy. Also, we mentioned at the top that we have recordings available. So if you'd like to review any of the webinars, you absolutely can. Please visit deltamotion.com, go to the education page, and then you'll see a link to webinars. They have their own dedicated page. You can see a list of recordings there with time-stamped topics. And then the upcoming schedule is also posted there. You can also find recordings at forum.deltamotion.com. You'll see a pinned webinar topic there. It has all the same information as the web page. Finally, there is a YouTube channel. It's Delta Motion Control, just like you see it there on the screen. Webinar recordings are there, and then there's some other miscellaneous useful content, examples of videos that we've shot just of demo systems and all kinds of interesting things there. So please feel free to check that out if you would like to. Thank you.
Thanks, everybody.